Are we live? Oh no. Hello. Hello guys. Welcome again to this today's live stream. So today I think we will be talking about a few ideas that I figured out uh, or talked to an LLM that helped me understand. Um, so last stream we talked about, we debugged, we did some live coding, and we found, let me just make sure everything is set and we're actually live. I don't know if, are we live? Yeah. Anyway, so we talked about a few things. We ran the model last stream. We trained the model but without plugs, some few plugs. We turned off some plugs. For example, we turned off RLS. RLS is recursive least squared, which helps the model learn online through adaptation and all the plugs that help the model learn or do well in the prediction in an online format. And what we found was that the model actually does well whenever we turn those off. And those that actually told us that the system is okay, but the way we are adapting the system or changing the system is not correct. And what I want to show you is that for example, we in our last configuration that was always failing. So this one was failing. And let me find the thing. So we have bandit predict order. Bandit predict order just tells the system that every time the environment changes, or you have to keep changing the environment after every 6 steps. Now that's not good because after every 3 steps. So countdown time 3 steps, you change the dimensions, you change the weights of the model, you change the dimensions, and that messes up the predictor. So the predictor assumes everything is new. In other words, it erases the memory of the model and then the model starts afresh. Now that's not what we want, because what we want is the model to keep learning and adapt throughout the system. Now and that's so to show you the results. So the results we found, let me just go back to. So this is I'll tell you about this, but let me go back to 34. 34 was um the configuration we ran for these is how many steps were these? These were 1,000 and so last stream I told you I'll be training the model for a couple of steps, like 200,000, and I did that. And let me show you the configuration for those 200,000 steps and the training for those. Do I have 34? Yes, I do. So the configuration looks like this. Same thing for this richer environment, and the only change here is we changed the learning rate to 0.0501. Initially, it was point. Let me see. Initially, it was 0.08. Now, what I found was zero point zero 0.08 just makes things worse in the sense that the model forgets faster, and every time we train it, it keeps forgetting faster than usual. So every history the model has been keeping keeps being forgotten when you have like a larger or a higher learning rate. And solution for that is keep learning rate at as low as possible. So one way we can do that is, well, I tried zero point zero 0.01, which did well. The learning rate, the model keeps improving when you have such learning rate. The other change here was, well, we added this was the fix that helped keep the model in keep the coherent, not blowing up like we had crazy values. I don't remember if I don't think I have it, but we had crazy values for our coherence. So sorry, is it coherent? Yes, coherence, which no, sorry, not coherence, but mean squared error, which kept coherence always going to zero. Now we could yeah, so the solution was just keep it within a small amount, so that we don't e e exponent doesn't just blow up and goes sends coherence to zero. And so now there's this one interesting thing that I found today when I was talking to an NLM was this order thing. So order was the order of so if think about the model we are using now, and then think about how we want the change to be ordered. So we have sensation. Every sensation is okay. Let me just show that to be just to make things easy and clear. So I'm doing something like wait, update update is it update or predict dot update. Yeah, so this is what I'm talking about. So I have these three orders, the order of, checking the prediction. So I have the previous X, then I have the current X, then the two previous X. So previous goes two steps behind. Now these are three. Now, and these values are being used in calculation of phi, or phi being the system, I mean the function that does help in prediction adaptation. So I'll open predictor, not okay, actually not there. So let's find phi is. So here the lags. So I have x lags. So expectation is it's a tuple, and so the predictor. Let me open where this is. So this is the predictor we are using. And predictor update. So this here. So we call this function in the kernel using x1, xt, which is the current time state, and then x2, which is two steps previously. And then we are passing um, just two of those. Now that's the problem. We don't, because we're passing two here, but our order says three. Where was it? Our order says three here, but we're passing two in our phi. Now, if you go to phi, you'll see what I'm talking about. So the everything that is not within the range of the order. So if the order, in our case, we have two in the code using two, but we have three in the configuration. So that's a mismatch in the order, and then the function tells the system, if you find a mismatch, just fill the rest with zeros. Now, if you fill the rest with zeros, it just means that the system will interpret those as noise, zeros as noise, and then just keeps learning, but learning the noise in the sense. So that's happening here. So we're only picking well, this is because one, because we already selected the first one here. Now one solution is So one solution is to directly just change this to one, or sorry, to two, so that it matches what's in the code. But well, that works, and I can show you how that works. So this configuration has the new configs, the new learning rate, and the order is still three. I mean, this is I was trying to test this now. Let me see. Let me just run it, and you'll see. So this is five. This is when the order is three. But let's try another run when the order is two, and then and what? So we also did a few changes. For example, I changed. Well, this is still off. This is what we want to try and solve today. This is off, always off. I'm turning it off, so there's no change in the environment. So the model is just doing a static is just training in a static environment, that not an interesting environment to run training in. So that's why it works. It works well, but we generally want to have a model to train in an environment that keeps changing, right? So we don't that tells us like the model is doing something interesting, because the world we want to be in is a changing world or environment. So this works, but with RLS, online training, online learning off, and the period is just fine. But I think we will figure out, we will change it somehow. Now, when we train this, okay, let's see, 20,000. Is it 20? Do you want 20,000 steps? Order is order is two. Now, so this is the simplest possible configuration. Learning rate is 0.1, and we have seen if you have learning rate predictors learning rate as 0.08 or larger, then the model forgets faster than it should. But if you have a smaller learning rate, then it doesn't forget as much. But let's train for this many steps with order is two. And so that's the simplest solution we can do. So change the configuration, and then the system will come back. And the other solution, which I think we will mostly do for this model to actually work well, is this. So since we are passing just the logs are just a tuple. It's a tuple of values, sensations. What we can do is in the kernel, because kernel just takes those three sensations. Now, what we can do is for our predictor, come on, I don't know. So our predictor, we will do an update. In the update, because we're only passing two orders, we can pass another one, say t, because it makes three. And I just did it while I'm still running on training. That's not good. That's not good. That's bad. I need to even wait. What? That's not good. Oh, I see. Yeah, yes, 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 yes. That's expected. Uh, I don't want to resume training. I want to start a new, fresh training. But um, let me train with order 2 just to see the effect of what order does. And then I will want to delete something here. I will want to delete. Okay. Do you want to delete 35? Yes, 35. And then we try to run these again. Okay, so the effect of order, and then without order. Okay, the mismatch of order and the match of order. So if you match the order in a specific, in the exact order number, then we will see the effect. And so that's one solution. Keep the order or keep the config as the code or fix the code. But ideally, at the end of at the end, we want something that's robust. We want, if we change the order, it should adapt. The code should adapt. So maybe we will, because I think in the kernel we are doing an update for we are just passing sensation. So I think I don't see anywhere we would have unless we are running a larger predictor, some large. We want to do senses or our sensation to be in order of magnitude larger than what we have here, like 3. We only have 2, 3. We're going back in time, you know, three steps. Say we want as much steps as possible, which for our research, I don't think we want that. That's overkill. But let's say we just keep this, and then we'll change the order to 3 and code to always adapt, to always use the same order we have. So in our predictor, I think yes, I think for the next run I will change the order from 2. Instead of changing the config, I'll just pass in, you know, the sensors, all of them. But why do you have 2 of them? XT. Hopefully it doesn't break. Anyways, let's see. Let's see if this works. Did I save? Oh wait, did I save? If I saved, something should change. But if we run this if we run the results, let's just see what the result looks like. It should not. It should be fine. But we can't do it when it's running. No way. Oh, I don't have these. I have that 5. Yeah, so this is it. So this is how it's training. It's doing. The coherent is not bad. It's still up there. 9.999 mean. This is what's slow. Coherent, focused coherent is slow. But pi tells the story. So pi just keeps, I think confidence has been gained for some reason. But we expect that because there's no change, there's no environment, weird switching of environments, just training um on static environment. Nothing is changing. We don't change the weight, we don't change memory. It keeps its memory, it keeps its dimensions. So we expect that. But what we want to do is we want a system that it's not just running on a static environment. It doesn't do anything interesting. We want a system that learns to adapt when the change in environment is detected. And And yeah, so let me just do this run again and change this to from our order to just back to 3 because that's what we had, and then keep the learning rate as is. And projected dimensions also, I reduced it to a smaller value just to keep the system in a stable form. Like it should not break. It should just be in that state. So we have the same order 3. Make sure what you passed 5 is exactly 3, and then config it should also be 3. Now we can run these again, and hopefully the results, I mean, there'll be a small difference because of randomness, but hopefully the results still perform well. The model still performs well. If it breaks, then we know the order doesn't really matter anyways. So yeah, let's wait for that. Then one other thing is, so I've been exploring an idea. Well, through from this bug, I will show a few. Okay, so I talked to an LLM, ChatGPT, about what we found, and I just want to read you the some of the thoughts it had, and we can explore these ideas that it has proposed. Let me start from when it started thinking. Yeah, here. And I'll just read through the proposed idea. The title of this stream is what's the title? The title is event modulated plasticity. So what does that mean anyways? I have no idea. Uh, but let's find out. So I looked it up because I the LLM suggested it, but it turns out in anyone working in neuroscience or computational neuroscience or anything brain science, right? You you might have come across something similar to event modulated plasticity, but with a different name. And what they call this is okay. Let me just read this. Refers to the form of neuronal plasticity, where changes in synaptic strength. That's what you call. That's the Hebbian learning form. So if you know about Hebbian learning, it's Hebbian. Let me. Did I just misspell Hebbian learning? Good. It's Hebbian. So if you're familiar with Hebbian learning, it relates to how synaptic strengths, how much synaptic strengths affect learning, and how much if it's weak, then learning will obviously be slow, right? But so let me just continue. Neuronal plasticity, where changes in synaptic strengths or neuronal excitability are influenced by specific internal or external signals or events beyond just the standard pre and post synaptic activity pairing. So what this means, like if you changes in the neurons or the strengths of a neuron can be influenced by external things. People use drugs to change the strengths of synaptic strengths. Some people use games. Games can also do that. Now, those are real things, real environment events. But what about our model? How do we how do we keep our model yeah our model in its like how do we make our model adapt based on events or changes in the events inside the model. Now we'll be exploring this idea and we will, oh, dopamine. So dopamine is strongly linked to reward prediction errors in reinforcement learning, effectively getting synaptic plasticity in areas like the stratum and prefrontal cortex. And yeah, so we will, let me just, no way. Okay, what happened? Um, how do I close this? I don't know how to close this. Okay, I think I can do this. Okay, right. So, no, Jesus Christ. Okay, so we will try this. Just modulation of. So we'll just read through all these interesting things, and now it turns out I was wrong, and maybe yeah, turns out I was wrong because it looks like it. If I unless I did not do it right, but see 35, I need 36. Yeah, I think turns out I was wrong. I was wrong. So I kept the config right, like we were supposed to have it, like three order. And then I passed three here, which seems to be wrong. We're still having this effect. Okay. So it looks like order doesn't really matter. I mean, it matters when you have the right plugins. I don't know if this is the correct XT, X1, XT. Let me just switch the ordering and see if this works. So XT to be the first. No, X2 to be the first. Hmm. And then, but will it? Okay, let's see. Where is it? Phi. Yeah, picks the first one. I'm assuming the first one is X1. Uh, and then for each, the rest of the order, you check if it's less than these, or supply zeros. Now we don't want to do this. Let's try another run and see. Okay, let's try this one. Oh, now that's too bad. That's too bad. Oh my God, it got to zero so fast. 0.0, and then goes up. Now it's playing around 0.6. Let's find out what's happening. Okay, so this is what's happening. Okay, okay, let's wait. Let's wait. I just have done something wrong. All right. How do we know? Goes to zero, then goes back up. Did it go back? Oh no, it did not go back. Just keeps going. Yeah. Oh no. So we need to figure out what the order should look like. Okay, okay, that's not good. Let me keep. Oh, I see, I see. I think I also need to do predict. Oh, I see. I don't need to do this here because x2 looks like xt is something else. It's not being used in x1, x2, xt. Uh, okay, let's keep this and then see. Yeah, it's still bad. Okay, I think the configuration's fine. It's fine. Because I need to also do here if I'm passing x x2 xt is the wrong value. Because you have two x2 x1 and 2. So I don't need to do it only in updates. I also need to do it in predictor, variance predictor. Okay, fine. Okay, let's do this. Let's just keep order 2 here and then explore. It's finished. Oh shit, it goes back up some point. That's promising. At some point it goes back to point 0.08. All right. Let's try this something else. So if we do projected dimensions to 64, learning rates. All right. Okay, then time. Now it's fast. It forgets so fast. Okay. Let's fix this. So, okay. Let me read through some things some things about. Yeah, I could read through this, but it's a lot. It's a lot of information. Mm, mm. But one thing I wanted to do is so there's some terms, sometimes some terms that this model, this LLM just talked to me about, and I want to, where are you? I want you to reason with me about them. Then we can figure out what to do from this. But yeah, so the idea is, yeah, I gave it the config that does the correct thing with the order switched, and it, you know, went on and talked about how it connects directly to real-time updates. It, so let me go to this last suggestion was about which one was it? Continuous event modulated plasticity. Now this is a new term I just learned today. Continuous event modulated plasticity. And looking up what this is. What is continuous plasticity anyway? So continuous plasticity is refers to methods. This is AI, so I don't think maybe it uses a different name, neu neuroplasticity or something like that. But this is AI, and I don't know how much we should trust this information. But continuous plasticity control refers to methods primarily in machine learning and neuroscience that allows a system to maintain its ability to learn new information over an extended period without becoming rigid or forgetting previously acquired information. Now, we have found this effect in our model. The system forgets, and then once it forgets, what happens is this effect. It just drops coherence. Coherence drops. Learning prediction just stops. No prediction is happening once it starts forgetting stuff. And we have found the reason for that is if you set let me open this. If you set predictors learning rate so high, then the model does forget a lot. Like it's like you're telling the model uh as, how can I explain this? So if you're telling the model uh the learning rate should be as fast as possible, right? Is it as fast as possible? Like the learning rate is higher than it should be. Like once it's so high, then what happens ideally is the model forgets the historical information, and we have seen that from the data. When we turn it, actually let's just make it higher and see the effect, and then make this as so keep the one that is okay, and the one that is okay is this. Did we finish? What happened here? Okay. So we want to keep the one that is okay. And then we want to, I just want you to see what's happening really. So I'm running this and this would be fine. Like the model trains so well when we have, it does so well when we have predictors learning rate as 0.1, 0.01, and then order is matched to what the order is expected. So the expected order for our phi is 1 and 2. So 1 and 2. And then we turn everything off. Dimension. Projection dimension is also reduced to a factor I don't know, half of the actual one, which was 64. Now these will train well with those plugins. And we can see from these results, I'll just print them so we don't, so we are not, vibing here. We see the results. Yeah, so this, coherent is not, it's not going to zero like we have seen. Um, and then, yeah, and pi is, doing its thing, just dancing, it's breathing, but dancing. And the mean. So the mean is also not broken. So I'll show you this when the learning rate is high, is low, as low as 0.01. And then I'll show another example where the learning rate is, we can change the learning rate to something maybe 0.05. So we are testing like which is the best range. Let's go to 1. I think 0.02 is another it's another good value to test. We can test with 0.02. Mm. We just want to figure out the best. I mean, we have already figured out the best learning rate to use, which is 0.01. And then we want to prove that it actually doesn't make the model forget stuff. And we can do that by adjusting the learning rate to another value and then do another training for 2039 and see if it breaks. If it breaks, then we will find the learning rate, the best learning rate. But let's see. Okay, 39. Okay. Okay, let's run again. Keep trying. Bear with me. We need to figure this out. Okay. So, doing okay, doing good. And break. Still good. I don't know at what point does it. I haven't tried this learning rate though. This is 0.02. 0.02. Okay. So halfway done. It looks like it's not breaking. Maybe that's still okay. The learning rate is not that bad. Uh-uh. Okay, let's try another one. 2 point, maybe 5. Let's try 5 and keep these as is. Just change the learning rate. See how the effect it has on the model. We just want to know if it forgets. So it's forgetting factor. And yeah, let me just read through. So continuous plasticity, man, it's mouthful for LS, and then goes on to talk about uh, plasticity gating. What is plasticity gating? Plus getting. Is it getting or get? Again, this is just AI terms. Unless there's something similar. This says stability by getting plasticity in neural networks. This is none. Let's read what this is. A temporal gating of acting remodeling during synaptic plasticity consists of the interplay between the kinase, no idea what kinase is, and structural function of, okay, modification of dendritic spines plays a critical role in synaptic plasticity. Modification. So think about how we are doing updates to our weight and updates to our dimension. which of course we have turned it off right now. So there is no sort of plasticity going on in the system. It just no change, no no updates. So I think molecule involved in this process through both kinase dependent and independent structural function. This is a nice read, but let's read the plasticity gating is refers to mechanisms that control when, where, and how much synaptic plasticity, our brain's ability to change, occurs. Oh, I see. I see. Okay, so if plasticity gating is because remember we in our model where is it? In our model we have something like we turn this off anyways. So let's find it. So this is off, bandit predict order. We changed it, we turned it off just because it breaks the system right here. Because this was doing updates in real time, changes the model every time. Now, what this does is it applies the predictor's order every time it sees something. It updates the dimension and the weight. So this function does that, and that's what we gave to our LLM, and it explained exactly what this system does, this code does. And we can see here we set everything to zero. We set the senses to zero, the previous sense to zero. We set the previous two sense to zero, and then dimensions also changes. And this observed dimension is what we have in our system as 128. That is what the observed dimensions are. Now, if we change everything every time we apply, we have a period of three. Every 3 steps, we are changing the model's memory or what the history just disappears. That's an effect that we don't want in our system. We want to change only if something happens. That's what we are calling event modulated plasticity. We want to change based on events in the system. So if an event in the system once, like I mean, happens, and then we want to use that event to change plasticity. I mean, to change the model. Because if you keep changing the model, then it forgets this effect we're calling forgetting factor or forgetting something, forgetting things. See, forgetting factors or something like that. And that's what we are finding from this is a neuron their brain's ability to change. We don't have a brain, it's just we are trying to understand how the brain works, right? So we can try to change these things, and we have found that we actually need event modulated changes, that is plasticity. And to figure out what events to change that's the next step. So how do we do that? Now it says how to do this. We can, instead of turning RLS on and off or changing order. Wait, did we finish the training for this? And it's still doing okay. Oh wait, did we run this? No, I don't think we did, because I didn't change this to 5. I need to change this to 5 and train again for 40. We just want to find out how learning rate affects this. How fast or how fast it should learn or slow. No, let's run these again. As this runs, I was just talking about this. How do we do this? How do we this? How do we do this? How do we do event modulated plasticity? Now, suggestions are which we have done. It's reduced to pi 0.0401, and then every step compute a scalar plasticity gating. So plasticity gating is, I don't know what this is, man. How can we do this in our model? It just talks about the brain acting like a gatekeeper to fine-tune learning, memory, and network stability. Often involved neurotransmitters like, this is just biology and stuff. Ion channels to adjust the brain's sensitivity to new experiences, preventing overload or maladaptive changes, especially during development or injury. Now, control learning is what we're trying to build, right? Like, how do we control learning? It determines the threshold for strengthening or weakening synapses, allowing targeted learning, like enhancing motor skills through temporary increasing cortical excitability, experience filtering. Our focus is control learning because we are building an adaptive controller that, if you put this code, this code in a robot, the robot can, learn to control itself without by just, using the code. I mean, the algorithm or what we're building currently. And then can drive drones with this. And once we figure out how to do plasticity gating, uh, sounds complex, but how do we do that? How do we figure this out? What else? So plasticity gating, that's one thing. We let's mark that. Do we have any papers on this? Temporal gating of active. Okay, so there is a in a inhibitory circuit gating of auditory critical pure. What is this? Come, cortical sensory nerve are remodeled during early life to adapt to their surrounding environments. Okay, let's mark that. Getting of hippocampus. Hippocampus or hippocampal, we all know it's something it controls or um, keeps the memory in check, or it's a memory bank or something close to that. So when you're dreaming or when you're consolidating memory, it's the job of the hippocampus to do that. And this says inhibitory circuit gating of auditory. This is auditory. This is for sound. Okay, plasticity gating mechanism. What's the mechanism to do this thing? A plasticity gating mechanism is a biological system that controls. Now we know this. Okay, so we have neuroplasticity. Synaptic changes can occur in the brain, ensuring stability while allowing learning, often by modulating neural excitability or activity. This is what we just found out. Anything to do architectures? Do we have any architectures for this? The term refers to the biological artificial mechanism that controls. Anyone working on this literal gating mechanism and plasticity of the beta barrier? So in our case, we use beta effective for plasticity. So if you look at this thing is what tells us how plasticity is And we compare this with pi, attention. And so if this is good, now this point on, we have done pi. Pi looks fine. Its attention is dancing, breathing. But how do we make this plasticity effective or better effective breathe, right? So that's our goal. And I think these people are talking about um, assembly machinery complex. Uh, okay. Insertion of the majority of outer membrane potentials, proteins. Oh my God. Okay, let's see. What else can we find out? Interaction between, there's another one. There is this one, interaction between circuit architecture and plasticity in a closed loop cell. Ours is closed loop, by the way, for your information. We have a closed loop, and by closed I mean we have an outer loop and an inner loop. An inner loop just controls, keeps the system in check, and then the outer loop just keeps the environment in check, like keeps focusing or paying uh or sensing, or just the outer loop is just what the environment looks like. We call them boxes, the box, and we call the inner loops as, water and fish and all that poetic stuff. But in this paper, they are, closed loop cerebellum system, what determine the sites and direction of plasticity underlying changes in neural activity. Behavior in a critical for behavior is critical for understanding mechanisms of learning. And I think once we figure these out, we have found out something about plasticity and how it affects the system. But our takeaway home is was it pi, or it was what we were looking at? What were we looking at? It was this guy. Learning rate, yes, learning rate. So learning rate is still fine for this case. That's not good. We need information on learning rate. Still doing okay. So we change this to 0.08 again. Let's make it 0.08 and see. There's some sort of effect it has. Ah, I see. Maybe we don't see the effect because the order was fixed or something like that. Maybe since we fixed the order, learning rate, um, okay, let's see this. If 8 does, 0.08 doesn't work, we can introduce a smaller a larger learning rate with some noise inside the system, that is like make order larger than 2, and try again. But as I was saying, so once we figure out plasticity, we need to see this curve doing something interesting as the data tells us. Because now we can't really tell what's happening here. It goes up, goes down, goes up. Um, Starts off well, goes down. I mean, by well, I mean it's at least not constant like this. Understanding learning. How do systems learn in a regime environment, in a non-stationary environment? Can they really learn? Uh, all right, so we've learned about this plasticity getting, but we haven't figured out how to code it in our system. Once we know how to code this, uh, so that's one thing. This is easy. Just change the config. We already have the configuration. That's what we're doing. Now we are here. How do we get this? Oh, we have residual z score. So I think it suggests we use residual z score plus chaos, but I don't know how to do that. I think I'll probe it some more. But we need to understand what this is, and we know what this is, and chaos is. Just yeah, I explained this a while back in the stream, and then we need to do some research on these plasticity getting, and how do we use the things we already have to do getting. And then there's another suggestion, which is temporarily scale the effective learning rate for the single update step. Now, the scaling could be easy, but we also need to know, how do we scale? Do we scale? Do we go high? Do we go low? How do we scale? Where's the this? So okay, we're still doing okay, which is okay, which is fine. I think it's fine. I think learning rate is doing okay for as long as don't for as long as we don't have a forgetting factor in the system. It's doing fine. Prediction is good. But once we introduce something for the system, um, oh yeah, so let's say we have a learning rate that let's make this, let's give the system something to forget, right? I mean, a way to forget stuff. We introduce these things and make learning rate as small as possible. See what effect it has on a system that has a forgetting factor, and make this 42, then 42. Now we have given the system something to forget. I mean, a way to forget. Let's just make it forget some information. And the order, as I explained, if you have two order, or the system just uses two order, and you give it three, then there is a window that is not covered. It's just that window is filled by zeros. Now those zeros just tells the system, learn noise, keep learning noise and forget. And then forget is, give it a window, larger projection dimension, so that it forgets. And then learning rate just makes it even worse. The forgetting is even faster than normal. Now we want to see that effect. We have, yeah, you see this broke the system already, even faster than it should not. Yeah, that was really fast. At step 1000, it broke. Okay, let's try making this 32, and then 32 and what? 41, 43. Let's see how how good or bad it does. Now, when does it forget? When does it break? Mm. Okay, 43. Where is it? 43. Yeah, it's still okay. It hasn't broken. That like we just reduced the window of getting the projection window to a smaller value. That's why it's not, it will break, but not now, hopefully. Not maybe after some few steps. Yeah, it doesn't break later until later on. Okay. Uh, Still okay. Okay, let's see. Still doing good. Come on. I want it to fail. I want it to break. Does it break? Oh yes, there you are. There you go. See, it was 1111, and after 14,520, it just goes to 0.009, and we can see that. So it's if you reduce the projection window, the projection dimension, it does do well at the beginning, and then after a few steps, just not few, but at least not as bad as when you have a large window, it breaks. Now, how do we know that how do we know that learning rate has an effect? Let's find out. So this fails at around 4,000, 14,000, and 500. Let's make learning rate as 5. Let's see when will this fail. Like, will it be earlier or later? And let's get this to 40, 44. Would learning rate be okay later or earlier? Uh, and let's compare, by the way. Let me open this on a let me open another file. Say lab what? Which one is this? Lab 55. Let's pick lab 54. Okay, lab 54, we want to log 44. And we want to compare these two. Sure. No, let me just do it here. So this is what we're running now. This is what we did before. So learning rate. Learning rate affects coherence. So we see this is 44 and this is 43. There's a huge difference. And after a few steps, when was it? Wait, what? After 10,000, it's later. It's before 14,000. So that's not It's not so big, but it affects the. How about pi? Although we don't want to focus on pi. There's after this is thousands. Yeah, it's a difference. But let's not look at this. Let's look at this guy. When does it fail? It fails at 10,600, and this one fails at 15 14,600. So there's a small window. Now, if we go higher, what happens if we make this higher? 44 and 0.08. Then run this. It fails. The more it's higher, it fails late. It fails earlier when learning rate is so high. The system fails early, breaks early. Let's find out if it's 0.08. Okay. Oh, no, we don't want to compare anymore. So when do you fail? Okay, let's talk about this. Right, so uh, yeah, we need to figure out how to do this to this too. And then example behavior, we don't want examples. Gives learning only when there's evidence you should learn. So this is what we're calling event modulated, without the need of full research grade. Oh, this is a nice research question. Like how can we build a regime or a detector that detects when we should be doing some sort of plasticity changes? When do we do that? How do we detect that we should be, changing these values? We should be changing learning rates. We should be getting plasticity. Like how do we detect that? If there was a way to, I mean, there is a way to do that, but it's a research question that we don't want to go through now. But it should be something we think about throughout this small thing we are doing. And then so it goes on to suggest a few things, but I think continuous or continuous. I was looking at this continuous thing. Continuous is just keep doing that thing, control every other step. When did it fail? When did it fail? Oh, it's around the same time. Okay, let's see it from here. This is step 45. When did it fail? It failed at around 13. Wait, that's strange. But yeah, is this is strange. 10, 13, 10, 13, 14. All right. Let's try again. Let's try small. We know the best one is maybe 0.3, 0.03, 0.02, 0.1. That we can just play around 0.01, 0.02, and 0.03, and let's keep this to this. And then This is fine. And so this is the minimum, maximum. This maps pi to beta, pi to plasticity, which is not really happening as we want it to. Okay, so time. So we've done what? We have done these two. We have done pi. We haven't done this, but we are doing some. We need to figure out what this is, how to do it. Application therapeutic. Okay, let's ask it. What is investigating? Now this would take 20 minutes to think. No, we don't have 20 minutes. Let's try something here. Plasticity. So there's something here. It said about kinase activity on channels, neurotransmitters, protein like, oh, this is proteins like CAMK2, calcium, dependent protein kinase 2 can temporarily get active mode. Yeah, that's biology. Shoot, wait, no internet. We are back online. No. We're still up. Connection lost. Hopefully we're still up. Uh, okay, okay, okay. That's not good. Okay, so let's see. Getting of hypercontractivity, plasticity, and memory by. Okay, got it. Long range inhibition. Long range inhibition. So long range inhibition, I think we have. This is what we're talking about order, right? I don't maybe. Uh, maybe yeah. So fine. Yeah, we can read about this later, but let's just keep. That's context getting neural networks. 2014. Through the context getting mechanism. Context getting. Is it the same thing as, wait, let's find out if it's the same thing. Okay, let's ask this guy. No, it would tell us yes or no. Maybe yes. Yeah. Plasticity getting um out of does okay, these are strong questions. Okay, this will take forever, so just wait. But it says this other one says the context getting mechanism is an architectural component in neural networks and neuroscience models that acts as a dynamic filter or smart valve. What? An intelligent device that automatically controls fluid like water or heating. Oh, to control the flow of information based on the surrounding context. So we have events, we have environment, we have the model. We know what plasticity getting is, at least some of the information theoretically or in principle, but we don't know how to write how do we write it in the code. Like we just know theories. It learns the selectively emphasize, suppresses, or combine different signals, allowing the system to focus on task relevant information. So just like okay, so if we figure out what plus how to code plasticity getting, I should stop saying plasticity getting, how to code this, then we can do something about context getting, because that seems like something else than what we are looking at. So let's see, let's keep going. Context. Where did we get context? Context getting. Oh, in the paper. Yeah, this is a neuromorphic hardware and human models behavior. The framework of context-gated spiking neural networks, CGSNN methods. In this section, we describe the methods. Okay, let's see what else we can find here. Learning independent getting of hippocampus, presynaptic getting of local and global getting. What maybe this can help. Mm, mm, mm. Two thousand. This is it still relevant? Because now information nowadays is really just, but yeah. Okay, next. We might want to look at Hebbian learning as another Hebbian theory as another form of learning. It's an attempt to explain synaptic plasticity. It's all about memory. And yeah, so if you want to listen to me talk about memory, you can go uh, to what from Institute channel. So I've talked about memory on this channel for a few times back. Let me just find. I don't know if I can find it here, but let me see if I can find it easily from this. No, I can't. I've talked about yes. So this. So here I explore memory augmented architectures specifically for biological for computations and what we have and what biology has taught us about memory augmentation. And I'll just maybe post this somewhere where you can find it. But here I explore memory. I also explore Hebbian learning too. So if you're interested in Hebbian, should I post it in chat? Yeah, I should post it in chat. So Hebbian learning. So that's where I explore. So if you want to see what something about synaptic, how the strengthening of the synaptic strengthening helps in learning, in neural networks and even in the brain. So Hebbian learning kind of explains this behavior, or Hebbian theory, not Hebbian learning, Hebbian theory. But what we want to do is know about Hebbian learning. And since we have hit the memory issue, then I think the best way is to talk about Hebbian learning, to study what Hebbian learning is. And wait, did we learn this? I don't think we were running anything. But yeah, so we will do something about we can do some next stream we can do something about this Hebbian learning. Hebbian, I can write Hebbian. It's Hebbian. Yeah, so what do we have from this? Oh, so yes, so this was 7 minutes. Okay. They are very connected. In fact, a lot of good online learning systems are basically context getting, which internal hypothesis memory expert is relevant right now. Memory. And then plasticity getting. How hard should we rewrite parameters given what's happening right now? This is the phenomena we have currently in the system. We want to figure out how well can we do this? How well can we rewrite the parameters, weights, and the dimensions? Then context getting is often the input to plasticity getting. Oh, so okay, so this is relevant. This is good information. So we need to study what context getting is and what plasticity getting is to figure out how do we make our system learn in an environment that keeps changing. So in our next stream, we will study that. So this is what we just turn off this, and then that will be online learning. That means we'll be changing the system. We'll be changing context of the system. That's what we're talking about, context of what we feed into the input that we feed into the plasticity gating. that's what will do this. So change this to true, and then the system will be changing its parameters. But we need to figure out how to remove this behavior because right now we are kind of making it forget, like making it forget every 3 steps. We don't want it to forget every 3 steps. We only need it to change if something changes, right? The context of the dimensions changes. The observed dimensions change, or the observed data. So yeah, so that'll be our next thing to do. And then memetics is already doing contextual plasticity. That's interesting because I think we haven't talked about memetics. We're still just talking about learning, but we will do evolution, how to evolve the best genome. So the best genome is we have a configuration for the best genome. This is evolved. This was evolved by me a few times back, but we can try to run an evolution of the best genome and use it in our system to see how it behaves. And then we will talk about memetics. Memetics is culture in the system. Like how do we will run a few systems. So there's a way we do training many agents at the same time. So if I go to a function and then training many agents at the same, it's called multi something multi agent. So this is what we will explore next, not next, but after we figure out plasticity, and then we can train agents at the same time and see how they learn together. So that's what we met. And these agents will be exchanging memes, and memes is not meme, literal memes, but information or compressed information for the system. And I guess that's it. So we have something to do next stream. And yes, I don't questions. No. Yeah, I'll put this link in the description so that people can listen to me talk about memory and all that, anything neuroscientific, neuroscience, neuroscience. All right, so let me add this into the description. I'll post it in the description before we before I before I exit. Anyway, so thank you very much for watching, and I guess I'll see you next time on end stream. Let me not make this a mistake again. End stream.